Hello everyone, this is the part 2 video to the exam 2 fall 2019 of MA 162. In this video I will cover the questions 7 through 12. For number 7, we're given a integral and we asked to use trig sub. So there we don't have to worry about what to use, and we're just to find the limit of integration. So keep that in mind, so we don't do too much work. So first, I will just write this down. 1 over, I'm just going to write it a little differently. T squared minus 2t. I'm going to try to complete the square here. Plus 1 plus 9. dt. So notice this first 3 terms of a perfect square. Something you should practice seeing, and that simplifies, that combines to t minus 1 squared, and 9 is 3 squared. And what I want to do is make a square root here so we can use trig sub. So I'm just going to square root that and square it. So it cancels out, but we can see there's a square root here now. Now I'm going to use sub u equal to t minus 1. Right, then du is just dt. And then the limit of integration would be 4, right? For 4 as t, for t equals 4, then u would equal to u equal to 3, and whereas 1 would be u equal to 0. Rewriting that, integrating from 0 to 3, we have u squared plus 3 squared, square root, and squared. Right, now we can draw a triangle for the trig sub. Now it's properly formed for trig sub. And we have u, 3, and this would be u squared plus 3 squared, square rooted. So now let's just say this angle is theta. Right, then we have relate theta and u as simply as possible. I'm going to use tangent since these are the two simplest parts. Tangent theta would be 3 over u, right? And then we don't need to go any further to try to substitute the square root part in and solving the integral, right? Because this, from here, we already have the relation between u and theta, which is what we need to get a limit of integration. So theta, for any theta, it would just be tangent 1 over 3 over u. So just the upper bound, which is the 3 for u. Plug in 3 here. Theta will go to tangent negative 1 of 3 over 3, which is tangent negative 1 of 1, which this is one of the common angles you should know. Tangent of 45, or pi over 4, is equal to 1. So that will be our answer for the question. But I want to kind of bring attention to, if we continue to do this, right, you'll notice that for the lower bound of the limit integration, it's 0. And if you plug 0 in u, it doesn't work, right? It's divided by 0. That's not how like algebraic math works, right? So one thing you can do is actually move this this theta over here, or you can write a different triangle, whereas you have this as theta still, but 3 here and u here. Then it's the same substitution. Well, it's similar, as in tangent theta would now equal to u over 3 rather than 3 over u, and now you can plug in 3 or 0. All of it will come out to be, proper math. But in this case, what the substitution for here, let me just write it in different color. It would be sine theta if I had original as this in theta. And then it would be 3 over the square root part. Here, it would just be cosine theta equal to 3 over the square root part, right? It's a difference of that. And at the end, you should be able to come up with the same answer, because once you can just substitute back for u for theta and then t for u, then you should still get the same answer. It's just that here, when you divide by 0, it doesn't really make sense. For number 8, we have a really complex fraction, and we are, to find the partial fraction expansion. So we don't need to solve this. And for the answer we see here, right, it's just a bunch of similar answers. You don't even need to do the partial fraction part, right? It's sort of like the polynomials are given to you. And we are even given the answer of this this integral, right? We just need to find the middle step, right? This is like step 0 here. You're given the equation. This is like the last step, right? You solved. We just need to find like the middle step where this thing comes from, this purple thing. And this is one of those questions where you can just work and really not work at all. Because you're given a fraction, you can say something like, if I take the derivative of this, right? If I take derivative of both sides, let me erase some of this. If I take the whole derivative of both sides, which I can do, dx, right? Then we have the dx of this. Then we have this. This is the part that becomes this, right? The integral is gone, so now we just have the fraction. And over here, when we solve this thing, whatever the derivative of this thing is, it would just become the partial fraction expansion. Is one way you can think of this, right? So derivative of this ln is just 1 over whatever in that ln, right? 5 over x minus 1 plus -3. Remember, the negative signs apply, and since they're doing the negative signs inside the fraction, I'm gonna keep that format, so it's easy to compare. Minus that plus -3, but I need to take consideration of chain rule. Right, so that would be just +3. Right, taking simple derivatives. And tangent -1 derivative is 1. You should remember, or maybe it's provided for you on the exam sometimes. It's like 1 over x squared plus 1. It's pretty useful. One I would recommend getting to know really well. So in this case, we have a 2 in front, which is going to put 2 on top, be x squared plus 1. Right, plus c is a constant, take a derivative, it becomes 0. So here is one way you could do it, right? So that would be answer A. But the other one is sort of it's sort of like just knowing this, where this comes from, right? If you can compare and just look at the answers, right? I can say this is gonna be like 1 over x minus 1. I'm gonna write it down, right? I see that this term is gonna match to this term, right? And this purple term here matches with this term. I should have the negative in there, right? And each of these terms matches each other. I don't know which one it is, but like it would be 1, 2, 3, 4, right? Each term matches with each other. So now I can just do process of elimination, right? So we have, if I take the derivative of this, it would be 5 over x minus 1. So immediately I can cross out d and e. Same thing with the second term, right? It's negative 3, which should remain, which ABC still remain. And then by the third term, I can say it should be 3, like here. Chain rule, always remember chain rule. So this is not right. It's not. There should not be a x term there, and it should not be negative 3, right? Although the last term, right, that they're all the same. It's just the third term that you can really compare and see which one is the right answer. For 9, we have a fraction, and to write it in form of a partial fraction expansion. So as we notice, this is a constant term. That means that after law of division, there will be something that was divided out. Since if you look at the power of the original fraction, the numerator and the denominator has the same highest power. So something will divide out definitely. And start with the long division. Probably need more space. So long division, x to the third. Actually, I need to write out the other terms. 0x squared plus x, 0x plus 2. And then we have the denominator, and since they're the same power and their constants are 1, so we can only place 1 here. And then we will have x to the third minus x squared plus x. Right, and then that will cancel out. That will be plus 2x squared minus x plus 2. Right, and that will be the a, the constant in front, and this will be the remainder that will go on top of our partial fraction. So we have 2x squared minus x plus 2 over, since it's given what the terms, the polynomials are, I'm just going to write it. Right, and this will differentiate to be that, or simplify to that. So let's see. Oh, actually, that's the linear term of this. So we can then list out the terms, multiply the polynomials, right? So b has to be multiplied by x minus 1 squared to be able to get back to the original denominator. So let's say b times x minus 1 squared plus c has to multiply the other two, right? X minus 1 and plus times x. So c x minus 1 plus dx will equal to this. So I'm gonna use a different color. And I'm gonna move this over here. So b squared minus 2, bx squared minus 2x plus 1 plus c, that would be x squared minus x plus dx equal to 2x squared minus x plus 2. see. So we have bx squared plus cx squared. I'm gonna keep the same power polynomials together now. Minus 2bx minus cx plus dx plus b equals to this. Right. And then use another color. We have the x squared terms, right? So bx squared plus cx squared equals to 2x squared, right? If you divide the x squares out, b plus c equal to 2. Again, doing that with the single powers that we have, negative 2bx minus cx plus d equal to negative 1, or negative x. We divide the x's out, this bit will be x, negative 1 x. And then finally, the constant term, b equal to 2. So, right, if we plug b equal to 2 here, so 2 plus c equal to 2, so x equal to 0, c equal to 0, and then plug both b equal to 2 and c equal to 0 in on the second here, then we have, scroll down a little, right, then we have negative 2 times 2 minus 0 plus d equal to negative 1. So d negative 4 plus d equal to negative 1, d equal to 3. For number 10, we're given 3 improper integrals, and we're to find out which of these are convergent. So for number 1, we have 0 to infinity for cosine pi x, right? This one, I would recommend, graphing cosine first, right? It's something like this, right? It oscillates up and down, and for if you imagine taking like a limit, right, for improbable integrals, you usually want to take a limit of like just the inside, right? If you solve this, it would be sine, but that's still the same shape, right? It just oscillates, but it's just shifted. Pi x, it would be 1 with pi. Something like this, it will always oscillate between negative 1 and 1, right? It's between this range, because if you can imagine, like the area of this would be like something like an area. I don't know what that area is, or I just don't need to find out what that area is actually. This is like the positive part of the area, and then the same part area will be sort of cancel out by this negative area, um, and then it goes to negative again, and then it gets canceled out by this positive. So you see that it's going really from like the integral goes like up and down a lot. So this oscillation just means that this integral will never converge because it's always oscillating to the end of the day. So number 1 does not converge. Number 2, we have, right, limit b equal to infinity, e x x e to the x squared. So we can just take the integral of that. It's chain rule. Then we will have what, limit b to the infinity of, that would be negative half. Equal to negative e to negative x squared 1 to b. And this, I found this easier if I write the negative powers in like in fractions. So I pull the constant out. We have limit of b to the infinity, and this would be e to the uh, x squared, or it would be 1 over e to the x squared, right? And then plug it in b for x. Then we have e to the b squared minus e, 1 over e of this. Right. And then if you plug infinity in here, this fraction goes to 0, right? If it's the e to like a power, if you think about like exponential graph, right? This is gonna approach infinity as x approach infinity. The y is gonna approach infinity. So it's 1 over infinity, so this is infinity small. It's gonna be, or rather it's infinity approaching 0. So this whole thing is 0, but there's still negative e to the x, which is a value. Therefore, this improper integral will converge. So right, check mark there. For number 3, we have quite an interesting case, in fact. If you graph this, you'll realize it looks something like this. Right, and if you don't know how this looks like, there's a pretty it comes with experience, but for I think about it as this will be similar to 1 of x. And since it's x squared, that means even the negative x will be flipped um, from down here, right? For a 1 of x, it will be something like this. But since it's squared, so this will flip up to be positive 2. Right. So it will probably look something like this. I'm not concerned with the values. I'm just really wanted to get the shape. So as you can see, from -1 to 1, this whole area there's a disconnect here, right? This goes to infinity. So it is improper integral. That means you need to use limits, and in this case, the simpler thing would be you can see that this is actually symmetry around 0. So you can um, take the integral from like -1 to 0 and then 0 to 1, right? And those will be the same since symmetry. You can just say 2 times the integral of 1 over x squared dx from -1 to 0. I'm just going to do that. In this case, I need to take the limit of to the approaching 0 from the negative side. Should be b. Right, and then solve the integral. That would be negative x 1 of x, right? Yeah. -1 to b, right, and then plugging b in. B -1 would be minus negative, so it'd be -1. And in this case, if I plug in, if I could take the limit of b approaching 0, right, it would be 1 over 0. This is infinity, or rather, the limit of this is infinity. right? Um, any limit divided of like limit approaching 0 will be infinity. So that means that number 3 does not converge. And that will bring us to 2 only, right? And then, I just want to talk about like a little test strategy. Maybe you don't know like um if this converges or not. Like number 1. And you know number 2 converges and number 3 doesn't. Right? The number 1 might get some people. I remember because I actually took this test. I wasn't too sure about this one either. Because it was oscillating and I was not sure about oscillating sums. And so I knew, right, C wasn't correct because it's 2 is correct and 3 is not. And 1 or 2 might be, right? This is not correct and this is not correct, right? And I took a guess. I was like, it's oscillating, it's probably not, but I'm not sure. But if you are able to get like 1 or 2, then use your options, right? And then narrow it down to an educated guess. Always helps. And this test is really long too, so if you can't solve all the equations or all the integrals, um, you know, do your best solve some of them and use that information to your advantage. For number 11, we have 3 different expressions or sequences. We define if they're convergent. Right, for these, we're just trying to, since they're all approaching, or rather have like an ending of infinity, what we can do is take the limit of this n to infinity and see if that converges anywhere, or is that if that's a value or infinity, then we can say if it converges or not. So for the first one, we have n 2n plus -1 over n, right? For this, we can just think about this -1 here, right? It doesn't really matter, because if you have like, let's say, it would just be -1, 1, -1, 1, right? When n gets really big, let's say n's 50, that's not really that big either. So it's like 100, right? 2 times 50, and then that would be +1. So what is this? This is like basically the same as 50 over 100, right? Which is a half. Right? This 1 or -1 is not going to affect much. Right? For 51 is going to be 1 or 2 minus 1. So that's like, it's like 0.499 or something like that. So something really close. But if we imagine this to be infinity, which is what the limit we're taking here is, then this -1 to the n, the 1 or -1 is not going to matter at all when it's infinitely big. So we can rewrite it as n over 2n. In that case, we can cancel that out, and this would be 1/2. And since there's no n in this equation, that would be 1/2. That means that this sequence will converge to 1/2. Another way you can do this is just writing it out, right? You can start from like n equal 1, n equal 2, 3, right? For n equal 1, we have 1 over 2 minus 1 is 1. We have for 2, 4 plus 1 is 2/5, which is 40%, 0.4. Right, 3, we have 3 over 6 minus 1, 3/5, 0.6. And then blah blah blah, go down to like, I don't know, a good amount, maybe like 8. So we have 8 over 16 plus 1, 8 over 17, 8 over 17, which is, let's see, just 0.47. That's getting really close. 0.47. You can kind of tell if you write this whole thing out, it's approaching 0.5. And the most important thing is that this is approaching a value, right? It would be like something like this before that, right? It's approaching a value. It's getting closer, right? It's going from like 1, 0.4 to 0.6 to a little bit under 0.5 to a little bit over 0.5. Kind of the general shape is going to approach a value. Therefore, the sequence is going to converge. For the second one, we have a sine. So again, take the limit of the n over to infinity. Right, what is this 2n minus 1 saying? Right, 2n minus 1 is generally, especially when you have integers, right? N being integers, that means that it's for n equals 1, this is right. This is 1, and then it will be 3 for n equal to 2, 5, right? These are all numbers, and then we have the over 2 is in here, so we have it'll be like sine over 1/2 pi, sine over 3 halves, 5 halves, right? If we graph the sine, right, for 1/2 pi, we have here, this would be, right, it go back to 0 at pi, and then it goes to -1 for 3 halves, and then goes back to 1 for 5 halves, right? So the values for the series is going to be what, 1, -1, 1, -1, and it continues to oscillate between these two values. And oscillation means that the sequence is not going to approach any specific number. Therefore, the series will not converge. So we have number 1 is converged, number 2 is the divergent, and now we can do number 3. Number 3, we have a of 1 is 1, and a of n plus 1 equal to the previous number divided by 2. So the simplest way to visualize this is actually just write out, right? We have a1, a2, and then we have 1, and that divided by a half, or divided by 2 is a half, and then a3 would be a2 divided by half, right? And then it grows smaller, smaller, smaller. And this is a trend that continues, right? This is just, it's going to go really, really small, right? As, let's see. So this is basically n, rather, 2n, right? And then it will be the limit of this over infinity, and this will approach 0 because the bottom here will be infinity big. Therefore, 1 over that infinity big will be approaching 0, the limit of that. So this converges because there is a value for that that limit to infinity. Therefore, the answer would be D. For number 12, we're to find the formula for a nth partial sum of this infinite series, and I'm gonna try to show you 3 different ways of doing this. Um, one is you have like a really sharp eyes and you have done practice to realize what this is, what this infinite series is, and the other 2 are sort of like you don't know what you're what to really how to really approach this, but there's just general tactics that will work most of the time if you don't know what you're doing. So first, the first method, right, this is a geometric series, if you can recognize that. Where geometric series are like if you have like something to the end, where it gets like 1/2, 1/4, 1/8, like that, or 1, 2, 1, 2, 4, 8, etc. Right? If you could realize that this n, you can add like a 1 to the end here, since it's all 1, and this is just the sum of 1/3 to the n, as in that's the geometric series you're looking at. And the partial sum of geometric series does have a formula. It is s equal to, or sk, let's say, for the kth partial sum, a 1 minus r k plus 1, and then over 1 minus r, right? R in this case is 1/3. It's sort of like the main growth value, and then a is in case there's a constant in front. In this case, that'd just be 1. Right, a equal to 1. And then k is actually the kth partial sum, but we need to be careful because this formula calculates for a infinite series that starts from 0. Would be like 1/3. Because this goes from like 1 plus 1/3 plus 1/9. So just keep that in mind, and we will need to minus 1 after that, so we can minus out this 1 that we don't have for this formula, since it starts at the first power of 1/3. So let's zoom in a little and just plug in the formula. Let's say Sn, the partial sum of the nth partial sum, will equal to a is 1, so we'll have 1 minus 1/3 k plus 1 over 1 minus 1/3 minus 1. Right. So here we have 1 minus 1/3 k plus 1 2/3. And what I'm gonna do is that I'm gonna multiply the top and bottom of this fraction by 3. Simplify it a little. So I have 2 in the bottom, 3 minus, so 1/3 times, take one of the 1/3 out, and it would be 1/3 to the k times 1/3 times 3. So these two will cancel out. Now I'm gonna bring the 1 up, the 1 that we subtracted from the sum earlier. So we have 3 minus 1/3 k, or it should be n. I plug m for k for all of the above. Minus 2, right? I'm bringing the 1 up. So then I have 3 minus 2, 1 minus 1/3 n, and 2 in the bottom. So now I'm going to try to simplify this 1/3 here by multiplying top and bottom by 3 to the n. Right, and this will cancel out. Every 1/3 would have a 3 to be multiplied with. So all of that will cancel out to be 1. I have 3 to the n, and then minus 1 over 2 times 3 to the n, which be our answer. I think it's option E. I will find that out, but let's move on to method number 2, I'll actually keep the geoseries formula in here because we might use it in a little bit in case that is used. Okay, for number 2, let's say you have no idea what to do. You stare at this and it's staring back at you. What I recommend do in that situation is that you write a couple of partial sums. You write a couple of the sequence down and then calculate the sums for that, right? So you have, let's say, n equal to 1, n equal to 2, n equal to 3, etc., etc. So then the numbers would be 1/3, 1/9, 1/27, 1/81, and then the partial sum, let's say S1 would be 1/3, S2 will be 1/3 plus 1/9, which in this case would be, that should be a 9. I was thinking about the answer. Be 4/9, right? S3 will be S2 plus the new one, so 4/9 plus 1/27, which equals to 12. 27 plus 127. Right. You write a few, and you kind of, what I kind of see is that here, right, whenever I have, let's say, S1, it's the bottom, the denominator is 3, which is 3 to the whatever partial sum, 3 to the n. Right, this is 3 to the 1, the denominator is 3 to the 2, this is 3 to the 3rd power, right? And the top part is sort of like it's kind of hard to see, but if you sort of expand this, right? This is um 1/3 plus 1/9, and if I have a common denominator of 27, then it'd be 9/27 plus 3/27 plus 1/27, like as in the S3, right? The common denominator is the S of n, and the sums we have on top, the numerators, are 1 plus 3 plus 9, which now is easier to see that this is a geometric series. As in, if you have like S4, it would be like plus 81, and the whole thing would be over 81, right? Or it would be plus 27, sorry. The next one would be plus 27. And then now we can use the geometric series summation again, except this time r equal to 3, right? And then we have a still is 1. Right, this is the numerator, sum of the numerators. So in this case, I have like, let's say sk will equal to 1/3k plus 1 over 1/1 minus 3. Right, this time we don't need to minus the 1 because it starts from 1. Right, we have 1 plus 3 plus 9. It's not 3 plus 9 plus 27. So we don't need to subtract the 1 here. And then sk will equal to 1 minus 3 to the k plus 1 power over negative 2. And I'm going to divide 2 on both of these. I mean, divide negative 1. So I sort of flip the sign. So we have 2 on bottom and then flip the signs on top. S of k plus 1 minus 1. Now, we kind of have to realize, let's say, I have S3, right? It's going from 1 plus 3 plus 9, right? This is 3, 0, 3, 1, and 3, 2. For 3, that means that the relationship between n and k is that n equal to k plus 1, or n minus 1 equal to k, because we have 3 for n, but the k amount that we're calculating um, really reach up to only 2. That might be a little confusing. But I would just double check like which, if you plug in k or plug in n, make sure that it's the right sum, because if it's off, then it's off by like a lot. So I'm gonna plug n for k now. It would be 3n minus 1 over 2. That will be the sum of the numerator, not the denominator. And then we can now divide by the denominator, which is, as we established, it's the denominator is 3 to the n, right? And then, so the total sum would just be 3n minus 1, 3 to the n power minus 1 times 2 divided by 3 to the n, which I can add to the numerator, which would be 3 to the n. A second way of doing this, sort of trying to find a trend, and then once you sort of gather the information, and then maybe you have better luck with it. Now the third idea is on, you're absolutely desperate to get this answer right. And it's just plug and chug, good old plug and chug. Since you have the formulas here, you have the sort of the partial sums you calculated for. Let's say you calculate that this one is 13 over 27, or rather that should be S3. S4 would be what? It would be 13 over 27 plus 1 over 81. So this times 3 be 40 over 81, I think. Right? I think that's right. Yeah, that's right. And then you plug every single one in for each answer. Since you have multiple choice, you can plug these formulas in and see if they're right. Right? Let's see. So for A, let's test A. Right? For n equal to 1, I have 3 to the first power minus 1 divided by 3. That is 2 over 3. That does not concur with my S1. So A is not right. B, we have 3 to the 1 plus 1, and 2 times 3 to the 1. So we have 4 over 6. And that is still 2 over 3. It's not right. B is not right. C is 1 over 3 of 1, which is 1/3, which is right. But then I want to test more, right? I want to test n equal to 2. For n equal to 2, C says that it's 1/9, right? But I have S2 as in 4 over 9. So that is still not right. Let me clear this a little. For D, it says that my S1 is 1 times 3, which is 1/3. Sure. For n equal to 2, I want to keep testing. It's 2 times 3 to the 3 squared. So that would be 1 over 18, which is not right. So that leaves with us with the only right answer. If you test 1, 2, 3, 4, if you don't believe, process elimination, maybe you did something wrong on A, B, C, D, maybe you can still test it and it will be right. Right? You can just plug in n equal to 1, 2, 3, 4 and test that partial sum since you calculated it already. And that is one way to do it without knowing actually how to do the question. Thank you for watching this video. The past exam archive and all the videos I did related to this exam will be linked in the description below. Please check them out if you're interested. Thank you.